Welcome back to the reaction zone. Today we're going to be looking at a concept that enables us to understand the behavior of gases. And that's the concept of Dalton's law of partial pressure. This law was named after a chemist whose name was John Dalton. And Dalton's law of partial pressure states that the total pressure that is exerted by a mixture of non-reacting gases is equal to the sum of their individual pressures or partial pressures. What this means mathematically is that if you have three gases, for instance, A, B, and C, and these are non-reacting gases, that the total pressure of these three gases is going to be equal to the sum of the partial pressure of each of the gases, which is PA plus PB plus PC, where PA represents the partial pressure with respect to gas A, PB represents the partial pressure with respect to gas B, and PC represents the partial pressure with respect to gas C. Having said this, it is important to understand what the concept partial pressure means. The partial pressure of a gas is the pressure that is going to be exerted by a gas if it occupies a container alone. For instance, if you have a tank that contains nitrogen and oxygen, these gases behave as if they are independent, they behave independently of each other. And the pressure that is exerted by each of these gases is the partial pressure of the gas. Dalton's law of partial pressure has real-life applications. It has real-life applications in the breathing of air and in the use of oxygen tanks in hospitals. The use of oxygen tanks in hospitals. Now let's look at the first one. We know that air is a mixture of gases. It comprises nitrogen, oxygen, and trace amount of other gases. Each of these gases in air has its partial pressure, and this affects how oxygen is absorbed by the lungs. The second real-world application is in the use of oxygen tanks in hospitals. Doctors mix oxygen tanks with other gases, and then they use Dalton's law of partial pressure to control how much of this gas or how much of each of the gases that a patient receives. Having said this, it is important for us to now look at the relationship between the mole fraction of a gas, and its partial pressure. Before we look at the relationship between the two, it's important for us to know what mole fraction means. The mole fraction of the gas is the ratio of the number of moles of a particular gas to the total number of moles of gases in the mixture. Mole fraction is represented by this symbol. The mole fraction of a gas is simply going to be equal to the number of moles of that particular gas over the total number of moles of gases in the mixture. This represents the number of moles of a gas. Whereas N total represents the total number of moles of gases in the mixture. Now that this is clear, we can relate this particular expression to the three gases that we are using for illustrations, which are gas A, gas B, and gas C. To find the mole fraction of gas A, it is going to be the number of moles of gas A over the total number of moles. The total number of moles in this case would be the number of moles of gas A plus the number of moles of gas B plus the number of moles of gas C. The mole fraction of gas B is going to be the number of moles of gas B over the total number of moles, which is the number of moles of gas A plus the number of moles of gas B plus the number of moles of gas C. The mole fraction of gas C is going to be the number of moles of gas C over the total number of moles, which is represented by the number of moles of gas A plus the number of moles of gas B plus the number of moles of gas C. Now, what is the relationship that exists between the mole fraction of the gas and partial pressure? The partial pressure of a gas equals the product of the mole fraction of that gas multiplied by the total pressure of the gases in the mixture. So, the partial pressure of the gas is equal to the mole fraction of the gas multiplied by the total pressure of the gases in the mixture. Using the analogy of the three gases that are making use of so far, it means that the partial pressure of gas A is going to be equal to the mole fraction of gas A times the total pressure of gases in the mixture. The partial pressure of gas B is going to be equal to the mole fraction of gas B times the total pressure of gases in the mixture. The partial pressure of gas C is going to be equal to the mole fraction of gas C times the total pressure of gases in the mixture. Please remember that this represents the mole fraction of gas A, this represents the mole fraction of gas B, this represents the mole fraction of gas C. This represents the partial pressure of gas A, this represents the partial pressure of gas B, and this represents the partial pressure of gas C. When you are solving a calculation that involves the use of these equations, it is important to know that the mole fraction of a mixture of gases, when added together, must give you 1. In other words, the sum of the mole fraction of all the components of the mixture equals 1. So, the mole fraction of gas A plus the mole fraction of gas B plus the mole fraction of gas C must be equal to 1, or approximately equal to 1. If in the course of solving problems with this formula, you add the mole fractions of the components of the mixture and it doesn't give you 1, it obviously means that there is a mistake somewhere. So you have to retrace your steps to find out where a mistake might have occurred. So this explains Dalton's law of partial pressure and the relationship that exists between the mole fraction of the gas and partial pressure. Please do not forget to subscribe and hit the like button in order to get notifications when new videos drop. Till then, see you some other time.